Hey, so this is Joe, and this is the first video for the 14th chapter in Stewart's Calculus, and we're going to be talking about the functions of multiple variables and the limits of these functions, and also, by extension, the continuity of these functions. So first off, we're just going to be talking about how we express a function in multiple variables and what that is. So in single variable calculus, you have a function that looks like this. You have some function of x, which is equal to some value of y. And our value of y, we call that the dependent variable. And because that value depends on our independent variable x, which is our independent variable. The difference between a single variable function and a function of multiple variables is the number of independent variables. So in a function of multiple variables, in 3 dimensions, it's 2 variables. We'll have 2 independent variables. And so these variables are independent of one another, but we have a third variable, z, which is dependent on both of these independent variables. So that's kind of how we think of a function of multiple variables, sort of a priori, right? However, and this being said, although this is kind of the limit of our capacity to graph a function of multiple variables, we also can have more than 2 independent variables. You can have an x, y, a z, a j variable, and that could equal some w, and we could have even 4 independent variables. You could have 3, you could have 5, depending on what you're doing. If you're doing some sort of complicated statistical analysis or whatever, you can have a bunch of variables in that function, those being the independent variables, and then 1 dependent variable. But generally in this class, we're going to be just dealing with 2 independent variables, and maybe sometimes 3 independent variables. So you should get comfortable dealing with 2, and then dealing with a third really is oftentimes just going to end up being more algebra for you to do. So this is kind of the algebraic, a priori concept of a function of multiple variables, but graphically they'll look something like this. So this is the function right here. So we've got our x-axis, our y-axis, and then our z-axis right here. This function would be expressed as f of x and y, because x and y are our independent variables here, and z is our dependent. It's z is equal to negative y squared plus x. And so we see that x and y are independent because this graph accounts for all values of x and y, all of them. And it's the z that changes based on those values. So you can say with certainty, so long as this function is continuous, and we're going to talk about that a little bit later, that there is going to be a point 1, 2, a point 3, 5, a point 6, 7, a point whatever. But what we're worried about is when those points, those ordered pairs, what value of z they equal. And that's kind of what we're concerned with. And all our functions will end up looking like little surfaces like this, except for the ones with 3 or more independent variables, because we don't have a nice way of graphing them like we do here. So that's kind of, in a nutshell, what functions of multiple variables are. Now let's talk about the limits of these functions. So in single variable calculus, when we wanted to find the limit of some function f of x, and we wanted to find that limit as x approaches a, we could look at some function, these being the coordinates, some function that looks like this, and we have our a here, and when we find that limit, we approach a from the negative direction and from the positive direction, and if the limit from the negative and the positive direction equals the same value, we say that this limit exists. Now that was pretty easy in single variable calculus, because since we're only dealing with 1 variable, we only have 2 directions in which we could approach this value a. We have the negative and the positive direction. But that's not the case in multivariable calculus, and we can see that on the graph over here. In fact, we can approach a value, some ordered pair x, y. We could approach that along the x-axis, we could approach it along the y-axis, we could approach it on the line y equals negative x, we could approach it on the line y equals x, but we could also approach it along curves, certain curves that go through whatever ordered pair we're trying to approach right here. So actually this would be AB. If we're approaching an ordered pair, we could approach it along many different lines on the xy plane. So it makes it a little bit more complicated to to prove that limits don't exist, and even more complicated to prove that they do exist. Because here we only have two directions. You can approach it in either direction, and if you get the same value, you know it exists. But in some cases, there are infinite curves that could go through a single ordered pair. And graphically, I'm going to show you what that looks like over here on our graph. So here we go. Once again, we have our function z is negative y squared plus x, and say we're trying to find the limit as this function approaches the origin, and so we'd write that limit out as x and y approaches the origin, so 0, 0, and so this indicates that x is approaching 0 and y is approaching 0 of our function f of x, y here. And so we could approach this value along the x-axis like this, along the y-axis like this, along the line y equals x like this, but there are also a bunch of functions that we could approach it along like this. And so what this tells us, based on this infinite amount of functions that we could approach that one value from, that if we approach this ordered pair 0, 0 from two different functions, so say we approach it from x equals 0 and y equals x, and we get two different limits. We get some limit 1 by approaching it like this, and some limit 2, and limit 1 doesn't equal limit 2, then we can say for sure that the limit doesn't exist. However, if you approach it from 3, 4, or even 5 different curves and you get the same limit, that doesn't prove that the limit exists. It indicates strongly that that limit might exist, and it might be the value that you keep finding, but it doesn't prove that it exists. And so a little later we're going to talk about how to prove a limit in multiple variables exists, but proving that it doesn't exist is actually quite easy. You just need to approach it from two different curves and find two different limits there. And so I'm going to give you an example of doing that right here. Alright, so we're going to start off with finding the limit as x and y approach 0 and 0 of x to the fourth minus 4y squared over x squared plus 2y squared. And so all we can do at this point is prove that this limit doesn't exist. So we're going to do everything we can to prove that. So, as I said before, we need to approach this limit 0, 0 from two different curves, and hopefully we'll get different limits there. So from single variable calculus, your first impulse might be to plug in these two values into their corresponding variables here. And that's a good impulse. If you just have a function that definitely doesn't have any strange discontinuity or anything at the point that you're approaching, you can very well do that, and you'll get a value, and you'll find the limit. However, oftentimes that's not terribly helpful. That's not a great use of our limit talk. That's really just finding a value of a function. So right here, we can plug in our 0 and our 0, and we'll get an indeterminate form, 0 over 0. Also, one option is doing some algebra and rearranging variables and having things cancel and then being able to plug in 0, 0. But this doesn't look terribly promising here. So we're going to need to use our two-curve technique. So the first curve we're going to use is we're going to find this limit approaching, and we're going to approach it along the curve, or the line I should say, x equals y. So that means we either plug in a y for all x's we see or an x for all y's. I'm going to plug in an x for all y's, and so we'll get a function just in terms of x, so all we have to care about is our x approaching a 0. So we're going to get the limit as x approaches 0 of x to the fourth minus, then we plug it in x for the y there, that'll be 4x squared, over, and that'll be x squared plus 2x squared. And so that will be equal to the limit as x approaches 0 of x to the fourth minus 4x squared over 3x squared. And now, when we plug in our 0 there, we'll get an indeterminate form 0 over 0. And since this is a function in one variable, that means we can use L'Hopital's rule. And so we'll get the limit as x approaches 0 of 4x to the third minus 8x over 6x. And we still get our indeterminate form here. So we'll use L'Hopital's rule again, and we'll get the limit as x approaches 0 of 12x squared minus 8 over 6. So now we can plug in 0 and actually get a value. And we'll get the value negative 4 thirds. So negative 4/3 is the value that is the limit we get. So that's equal to our little L1 right there. The limit we get when we approach this limit, or that ordered pair, along x equals y. And an important thing to remember is whatever curve you're approaching this along has to go through this ordered pair. And 0 equals 0, we plug in a 0 for the x and the y, we're good. That line goes through that point. So now we're going to have to try approaching this from another curve. And let's try approaching it along the x-axis, so along y equals 0. And so that means that we're going to be plugging in a 0 for every y we see. So, and again, we'll get a function just in terms of x. So we'll get the limit as x approaches 0. And also, when y is 0, x is also going to be 0. There's a value that exists for this function. So we're going to get the limit as x approaches 0 of x to the 4th. We put a 0 in for the y, and that becomes a 0 over x squared, and likewise we have a 0 right there. So this is going to be equal to the limit as x approaches 0 of x squared, and that is equal to 0, which is equal to our L2. So because 0 is not equal to negative 4/3, we have L1 is not equal to L2, and therefore the limit does not exist. So that's how we prove that a limit in multiple variables doesn't exist. And that's kind of the easiest thing to prove with limits in multiple variables. Now we're going to talk about proving that limits in multiple variables do exist. And this is a little bit more tricky. And we'll see why here. Alright, so here are our 3 ways that we can prove that a limit in multiple variables does exist. So first off, this is the real simple one, kind of the most obvious. If you have a limit and you can cancel out one of the variables and make it a limit in one variable, do that, because that's going to be your best bet. And really, if you can cancel out one of the variables, that means that the limit isn't actually a limit in multiple variables. There's just kind of this pseudo variable floating around that you can cancel out. And so most of the time in this course, that won't be the case. You're not really going to have to, I wouldn't recommend looking for that, or kind of trying to force anything out of an equation that you won't be able to cancel a variable out of. Second, you can use the Squeeze Theorem. If you remember from single variable calculus, if you have some function that passes through a value and some other function that passes through a value, and the function that you're looking for is always in between those and is kind of squeezed like this and passes through the same value, the limit of this middle function, if the limit of these other two functions are the same, the limit of this function will also be the same. And so that works also in multivariable calculus. If you can get two functions that are kind of similar to the function that you're trying to find the limit of, you prove that the function you're trying to find the limit of is always in between these two functions, so greater than or equal to these two functions in between them. And these two functions on the outside have the same limit at that value you're trying to approach, and that means that that function that you're trying to find the limit of also has that same limit. But that's a little bit, not that it's just complicated, it's a little bit unlikely that you'll be able to get two functions that are kind of similar to the function you're trying to find, and that squeeze that function. That's a sort of unlikely scenario, but if you can find that, go for it straight away. But most of the time what you're going to have to end up using is this sort of delta and epsilon talk, or this delta and epsilon method, which I'm going to describe in the next slide because it's a little bit complicated. It takes a long time, but it's effective. So here we go. So what our delta and epsilon method tells us is if we have a limit, and it's the limit as x and y approaches some a and b of some function of x and y, and we suspect that that limit is equal to some L, and that suspicion can be founded upon using 2 or 3 curves, sort of odd curves, to approach this limit from, and we keep getting the same value. If we suspect that this L is going to be something, we get that something, and we say, alright, if we have some value delta that's greater than the radius of the circle centered at a and b, so this expression right here, which will also be greater than 0. So we have some delta that's greater than that circle, and we have some epsilon that's greater than the absolute value of the distance between the function x and y and the suspected limit, which will also be greater than 0. If these two things hold, then the limit then our suspicion is correct, and our limit is that thing. So there's a proof for this, but intuitively what it is we have the value that we're trying to approach on our surface right here, A and B. And what we do based on this delta is we take a circle around it, and what this epsilon is doing is finding values that are approaching it and approaching it and approaching it, and eventually we'll get one limit that will be a value of z. That's what the limit will be. It's a z value, right? And so that's kind of how it works. But in order to use this method, we first need to use our curves method, our approaching by multiple curves, to get a limit that we suspect. So I'm going to go through one of these problems with you, and it'll take a little bit of a long time, but it's worth it because this is a kind of confusing thing. So we're going to do number 13 on page 923 in your book, and it asks us to solve this limit as x and y approaches 0 and 0 of this function right here. So first we're going to try to approach this limit along the line y equals x, and y equals x that passes through 0, 0 right here. So along y equals x, we're going to plug in for each of our y values, we're going to plug in an x value. So what we get is we get the limit as x approaches 0 of x squared over root 2x squared, like that. And this will give us, so from here, what we can do is we can use L'Hopital's rule, because we get our indeterminate form right here, and this will become the limit as x approaches 0 of 2x times the square root of 2x squared, and that comes up from the bottom from this, because that becomes a negative square root, right, over 4x. And that still gives us our indeterminate form, so we have to use L'Hopital's rule again, and we'll get the limit as x approaches 0 of, and then we take our derivatives here, and we're going to get a half, and then a root 2x squared, and that halves comes from taking the derivatives of each of those two sides right there, and presto, we will get that limit is equal to 0. And so that right there is our little L1. And so now we're going to try to find the same limit along a kind of weirder curve. That curve is going to be the parabola y equals x squared. So we're going to put an x squared in for every one of our y's. And so that will become the limit as x approaches 0 of x cubed over root x squared plus x to the 4th. And so now we get L'Hopital's rule and we plug in 0 for x. So that will give us the limit as x approaches 0 of 3x squared times root x squared plus x to the 4th over 2x plus 4x cubed. And we still get our indeterminate form here, and so we're going to need to use L'Hopital's rule again. We're going to get the limit as x approaches 0 of, and this is nasty using the chain rule, we're going to get this plus 3x squared times x squared plus x to the 4th to the negative 1/2 times a half times 2x plus 4x cubed. We're going up the page a little bit there. All of that over 2 plus 12x squared. Whew! Okay, so that's a lot of limit work right there. And so now we have a constant in the denominator. And so it looks like this whole thing is going to equal 0, and it will. However, we have this negative exponent right here, so this is really a 3x squared over x squared plus x to the 4th, and that's a radical. And since there's a radical in the denominator, if you take that isolated thing, the limit as x approaches 0, that limit will eventually be 0, and we can kind of see that based on what happened up here. So this is going to end up being 0, and I'm not going to show you that right now. And the rest is at 0. So take my word for it, this limit's going to end up being 0, and you can do the rest of the algebra like that on your own. So we have our L1 is equal to our L2. Oops, sorry, it's an L2. And these are two kind of out there curves. And so we can say, all right, I suspect that our limit is going to be 0. And that is my suspicion, and I think it's well founded. So, given that, we can go on to use our delta and our epsilon talk. Now that we've got our limit suspected to be 0, we can do our delta epsilon talk. So we've got 0 is less than the circle with the radius about the values that we're approaching, so that's just going to be x squared plus y squared, square rooted. That's going to be less than our delta. And our function, so this thing right here, the absolute value of our function is going to be greater than 0, and it's going to be xy over x squared plus y squared, minus the limit we suspect it to be, so minus 0, should be less than our epsilon. So now we need to start proving this. So first off, we've got that, so this makes sense. These values will always be positive, no matter what. And this is going to always be greater than 0 if x and y, so long as x and y aren't 0. And we can, and so that's kind of what we need to prove. We have to prove that x and y, we want to find the limit as x and y approaches 0, and so that's where the epsilon talk comes in to kind of show that this will always be greater than 0 and won't really be 0. So what we have to do is we have to kind of put all this in a continuous chain of inequalities, or that's how I tend to do it. So we have right here, we know intuitively that the square root of y squared, which is really just y, will always be less than the square root of x squared plus y squared, and that is always going to be less than our delta right there. Makes sense? And we can also say up here that x, the absolute value of the absolute value of root x squared plus y squared is going to be root x squared plus y squared. So we don't need the absolute value of ours there. And the absolute value of root y squared, or the absolute value of y, is going to be the same thing as the absolute value of root y squared. So we have absolute value of x, root y squared, root x squared plus y squared, and that is going to be less than our epsilon right there. And so we can multiply some things over. We've got our absolute value of x times our root y squared is going to be less than root x squared plus y squared times epsilon. And now we have already here an expression with our root x squared and our plus y squared. So, oh yes, and also what we have to note is that this, we're calling this y squared greater than 0 also. So, given that, we could start putting these things in a big chain of inequalities. So, assuming that this root y squared is going to be greater than 0, we have root y squared, and that's going to be less than. So first off, if you have any constant times this root x squared plus y squared, you know that it's going to be bigger than just the root x squared plus y squared on its own. So, root x squared plus y squared, and that's given that this is a positive constant, right? That's going to be less than root x squared plus y squared times epsilon. And it's going to be less, and that will be less than our delta, and this will be greater than the absolute value of x times root y squared, right? Because this is greater than that, is less than that, and this is greater than this. So we have this whole big continuity of things, and we have, in any case, however it turns out, we have our epsilon and our delta are both always greater than 0 in this case. So that means that the limit, really, our suspicion was correct, and our limit is 0, and this proves it. So that's it for finding limits with multiple variables. I hope you stay tuned for the rest of this chapter. We're going to start talking about partial derivatives soon, and it's pretty exciting, so thanks for watching.